Good afternoon, everybody. Thank you so much, Ari, for the kind introduction. I'm going to talk today about cryptoeconomic security for arbitrary tasks. I'll start with motivating this talk with some of the work we are doing at Eigenlayer. So if you think about the evolution of blockchain, our thesis on blockchain is it's a mechanism to create more permissionless innovation or open innovation. And if you look at the various layers of a blockchain, you see basically there is a security layer at the base, and then it could be staking or mining, on top of which there's a consensus layer. Nodes come together and arrive at consensus. On top of which there is an execution layer, like an execution environment, like Bitcoin script or EVM or whatever. Then applications then build on top. Bitcoin was an application-specific blockchain designed for storing, sending Bitcoins. So you had all these 4 layers, and they were all tightly coupled and integrated. And Ethereum was the first modular blockchain. Modular in the sense that anybody can build new applications on top of a common substrate of security, consensus, and execution. So this led to a whole growth of dApps. Anybody coming and building new kinds of smart contracts on top of a common trust platform. And then you go to the next framework. I think you look at rollups. Rollups, basically, anybody can come and build new execution environments on top of a common consensus layer. Each rollup runs its own off-chain execution and makes proofs that it did the execution correctly. And so now you can have innovation at the level of execution environments. You can build many execution environments on top of a common consensus and security layer. And what we did with Eigenlayer, I used to run the University of Washington Blockchain Research Lab, where we worked a lot on consensus protocols. I also have a bunch of papers with Ari on FAR ordering and consensus protocols. Let's say you want to go build or deploy any one of them. You don't have root access to go change it on Ethereum. So this is really why we built Eigenlayer. We built Eigenlayer to modularize security. It just does security, on top of which anybody can build new consensus layers, on top of which other people can build execution layers, application, and so on. So it is the deepest level of open innovation. So now you can basically build anything. So just imagine an abstraction. It just covers decentralized trust or security. Now anybody can come and build new kinds of networks, protocols, which require you to reprogram how the network works. Okay, so we call these consensus layers built on top of Eigenlayer. So Eigenlayer is the name of the protocol that we built. And it's a system for shared security, a common security layer for any decentralized network to be built on top. These networks, we call them AVS, actively validated services. Actively validated means somebody is actually running nodes to keep these things going. Services rather than chains, because we think of service as the right unit of operation. You may be sitting on Ethereum and you want to make a call to an AI engine, and you get a return, which is the executed output of this AI inference. That's a service. It's not necessarily a chain. Okay, so that's the setup. Now you ask, how do you provide security? And in this talk, I'm not going to talk much about the sharing part, which is how do you extend security to multiple different systems, but I'm going to focus on what is the right framework for providing security. So, the core idea in Eigenlayer is cryptoeconomic security. What is cryptoeconomic security? You have a bunch of nodes which commit stake. They all commit some stake. Stake is just take a bunch of digital assets, ETH or something else, and then lock them up into a contract. And once you lock them up into a contract, now you promise to run various services, various AVSs. Okay, so that's what's happening. And the main question is, when you have permissionless validation, anybody can come and run validators, how can you make sure that these validators are doing the right thing? And the core idea of cryptoeconomic security is if nodes fail to perform the task in the way they promised to do it, then they'll lose their stake. So that's the check and balance for how cryptoeconomic security works. Okay, so, once you look at this, you can ask the question, do we need cryptoeconomic security? Are there other ways of doing security? And should we use the best possible one? And so to do this, we came up with a taxonomy of what kind of properties you want from systems and how we can use different mechanisms to achieve these security properties. So a group of nodes come in and they're running some task. And what you want to do, I said in cryptoeconomic security, if they did the thing wrongly, so which means they committed a fault, they should be punished. So what kinds of faults are we talking about? The first category of faults is objective faults. Objective faults means you're violating some objective condition. Think of it like a mathematical or a cryptographic or like a deterministic code execution. So the first category, subtype of objective faults, is we call it proactively attributable. What does proactively attributable mean? I run a piece of code, and then I can attach a proof that I've actually run this piece of code correctly. So as soon as I give you an output, I can give you a certificate that I've done that output correctly. And when you're running an execution, so you can use something like zero-knowledge proofs, which is basically what we call in our space, but really verifiable computing, which is you can create short proofs of correct execution. You can use either zero-knowledge proofs, or you can use cryptoeconomic security. CE stands for cryptoeconomic security for this. But ZK is probably better. And a lot of people think maybe ZK is all you need. You don't need anything else. All you need is cryptographic integrity to do all these tasks. I'm going to argue it's absolutely not the case. So the next category of faults is what we call retroactively attributable. They're still objective, but only retroactively attributable. What do I mean by that? Imagine I sign to the protocol says you should, validators should sign off on only one block for block number 30. But a validator goes around and signs 2 certificates for block number 30. This is a violation of a core covenant of the protocol. But I cannot give you a certificate that I have never signed another block with block number 30. Because this is not an error of commission, this is an error of omission. I've given this other certificate to another counterparty and trying to fool everybody. So, but retroactively, after I did this, somebody can, get both the certificates and prove objectively by showing me 2 certificates that Sreeram signed on block number 30 is H, but block number 30 is G. They're not the same, so he should get slashed. So it's objectively attributable, but only retroactively. You cannot do ZK for this. There is no cryptographic proof of integrity for this. Except in quantum computing, you can use the no-cloning theorem to do this, but we'll skip that for here. So this is, we call them reorgs or double signing or whatever. And these faults, you need cryptoeconomic security. I have a bunch of stake. I promise that I will not do this error of omission, like that I will not sign 2 blocks with the same block number. And if I do, you can catch me and slash my stake. Okay? So first argument for why ZK is not the end game. ZK is not the end game for building blockchains. We need much more interesting, more important fundamental primitives, or equally important fundamental primitives to actually make these systems work. Okay, what else do we have? We have a category of faults we call intersubjective faults. Okay, fancy name. What does it mean? Intersubjective. Subjective means like I have my own opinion. Intersubjective means we can all socially agree. Another way of thinking about it is these are faults for which there is off-chain agreement, but not necessarily on-chain agreement. Okay, so I'll give you an example of a fault. We say, who is the president of the United States? Who won the silver medal in swimming in the Olympics? Examples of questions for which we have off-chain, social, intersubjective agreement, but on-chain, I don't know. There's no locus to bring the right sense of truth on-chain. So these, we call them intersubjective faults. So when you think about intersubjective faults, we still categorize them into 2 types, retroactive. And an example of this is, an Oracle price feed, let's say. I come in and say, 1 BTC is equal to 1 USD. 1 Bitcoin is $1 US. It's absolutely not true. We all know. But on-chain, somebody said it. Now, what are you going to do? How do you know it's wrong? We don't know on-chain it's wrong, but we know off-chain from the outside frame of reference that it's wrong. So this is an example of intersubjective fault. And it's retroactively attributable. Depending on the scale of the error, it's retroactively attributable. I can come back in 3 weeks, and if I said 1 BTC is 1 USD today, you would still know that I said the wrong thing 3 weeks back. So intersubjective, retroactive. Okay, so the next category of false we call intersubjective concurrent. Concurrently attributable. Concurrent basically means you had to be there at that time to know that it was a fault. One fault that we think about a lot is data publishing or data availability. I have a network of nodes which are storing the data, and they're promising that we will allow anybody to download the data if they ask for it. It's called data availability. Is AVS that we are building called EigenDA. Okay, so in EigenDA, these nodes promise that they're going to serve the data to anybody who asks for it. But how do you know that they all didn't collude and never serve any honest node ever? Even if they served one honest node, that node has the data, they can go and stand up a website and let anybody else distribute the data. But what if they never served even one honest node? This fault is not observable on-chain, but it's observable off-chain. Anybody who's querying the RPCs, anybody who's running a full node, anybody who's connecting to the peer-to-peer network, all have a locus to know whether data was published or not. This is an intersubjective fault, off-chain observable, but concurrent. I need to be there at that time to know. I can't come back 1 week later and know whether the data was published this week or not. Because I may have withheld the data this week and publish it 2 weeks later after whatever fraud-proof window or other important time horizon lapses. So it's a concurrently attributable intersubjective fault. So this is the topography of the various kinds of faults. There are also non-attributable faults. They're neither on-chain attributable nor off-chain attributable with high social concordance. An example would be you take a data item and then spread it into secret shares, like Shami's secret sharing, many of us would have read. So you take the data and then split it into secret shares and send it to a network. Now, if a majority of the nodes met together in a private boardroom and revealed the data to somebody, there's no way for us as a society, as outside observers, to get social concordance on whether that happened or not. So this is not even intersubjectively attributable. So these are the various topography of faults that we came up with. And the question became, how do we create cryptoeconomic penalties for intersubjective faults? To go into this, I want to specify a meta framework for coordination. Whenever you're thinking about who is enforcing these conditions of coordination. So think of this like the fact that you don't want certain kinds of faults, think of this as basically like a condition of coordination. I'm a validator, I've opted in, I've promised that I will not make these faults. Now, who's enforcing this type of coordination? You think of like broadly at like a macro scale, 4 types of coordination. You can have an authority that enforces the condition of coordination. You can have a committee that enforces the condition of coordination. You can have a majority of some group of nodes that enforce the condition of coordination. And then, and each of them are more robust than the previous one. And then finally, I think you have the gold standard of coordination I call self-enforcing coordination mechanisms. A self-enforcing coordination mechanism executes itself irrespective of what anybody says. Neither an authority, nor a committee, nor a majority can come and corrupt the condition of coordination. So that's what we call self-enforcing coordination. So I'll illustrate this with an example in blockchains. You know, a lot of the theory that we do as academics in blockchains usually stop with majoritarian coordination. We assume a majority of nodes are honest, what properties can you brew about a consensus protocol, and so on. But the really powerful thing in blockchains is you can go even beyond that to self-enforcing coordination systems. Imagine like you're running a blockchain protocol, and a majority of validators are malicious, and they sign an invalid block. They sign a block, the state transition function is not computed correctly, they sign off on a block. Okay. So this is a majority malicious behavior. And you know, in a protocol like Ethereum or Bitcoin, the condition is that if the block is invalid, it doesn't matter even if a majority signs off on it. You don't accept it. You don't accept a block which is invalid, which means you fork around it. So you fork around it means somebody else will include the certificate claiming that a majority were malicious, and then they can continue. Only the remaining nodes are now eligible to participate in consensus. They come to consensus, and then they can actually proceed forward based on this system. So this is a self-enforcing coordination for validation, for execution validity in a blockchain. You don't need to trust a majority. If a majority does the wrong thing, signs off on an invalid block, they'll get slashed, they'll get removed from consensus later. Very, very powerful system. So blockchains are not correct based on a majority of the nodes. They are self-enforcing. Okay, so this I'm specifically talking about for execution validity. So we have to take each fault that a blockchain can perform and make sure we can recover from that even when there is a majority fault. Okay, I'll skip ahead and start the question. Okay, so this is true for execution validity. Right? Go back here. If the execution was wrong, then yes, you will fork around it. But what if inside this Ethereum block, there was an Oracle price feed or an EigenDA feed or some other AVS brought in a wrong data? We can't fork Ethereum. Ethereum has we don't have any license to fork Ethereum for things that happen on the application layer or on the Eigenlayer or any AVS layer. Okay, so what do? This became the big open question for us in resolving how do we solve faults which are socially, intersubjectively, off-chain attributable, but we want to enforce this not based on an authority, not based on a committee, not based on a majority, because they all suffer from the tyranny of majority. You know, a majority of the committee could lie, a majority of stakers could lie, so we don't want to trust any of them. We want to enforce it only to truth, not to power. Okay, how do you do this? So, you know, the methods people have are majority voting, like you have a majority of stakers vote on something, you can have a committee vote on something, but you know, you have to ask the question, what types of coordination mechanisms are we building? How do we make them very robust? And both of these are vulnerable to the tyranny of majority. So the only system that's really robust to the tyranny of majority that we know about is forking. Okay, but as I said, the problem is, so what's happening in forking is if there were two forks of Bitcoin or Ethereum, people figure out what is the right fork because they know what the execution conditions are. It is self-evident what the right fork is, and so people automatically gravitate towards the right fork. Okay, so you can think of forking as like a social consensus on an unsized and unbounded group. Like you don't know who these people are. Anybody who's coming behind you is going to decide what the right fork is. So this is the only system that is robust to the tyranny of majority. So we call these self-enforcing. So the question is, how do we extend cryptoeconomics to any intersubjective fault without forking the chain? Because Eigenlayer is built on Ethereum. We have no license to fork Ethereum. What are we going to do? Okay, so that's the main problem. So I'm going to illustrate a couple of key ideas and then put together the solution for you. The first idea is when we're talking about forking, a lot of people have this idea of social consensus as ad hoc, post facto, capricious. We meet on Twitter and then say, oh, that guy is bad, I'm going to fork him. That's not a good system. It's a kangaroo court. You want to have a system where it's preset. There is a setup phase which presets what the conditions of forking are, and then an execution phase where you just follow the pre-agreed conditions. You fork on pre-agreed events that are self-evident. Two words, pre-agreed, self-evident. So you only fork on pre-agreed events that are self-evident. Okay, one thing that gives us a good match here is when we're talking about self-evident, intersubjective faults are self-evident because they're off-chain observable. So that's a good match of what framework we're talking about and this core idea. The second core idea is, as I said, we're building on Ethereum, we have no right to fork Ethereum. What are we going to do? We create a new idea we call token forking. Okay, so here is a meta point. I said the faults are intersubjective, which means socially, off-chain, it's observable whether it's a fault or not. There's another thing which is intersubjective, which is the value of a token is intersubjective. We all look at a system and say, suppose I take Bitcoin and fork it and create another chain. Are you going to say that that's worth $1 trillion? No, you'll say the original one is worth $1 trillion. This new one is BS. That's what you're going to say. Value is intersubjective. Truth, social truth is intersubjective. You merge these concepts. So that's the basic idea. Okay, how do we do this? The core idea is instead of forking the chain, which we have no license to do, fork the token. What do you mean by fork the token? So, you're chugging along, you've staked the eigen token on Eigenlayer, and the system's chugging along, and then a majority of eigenstakers turn malicious and report that 1 BTC is equal to 1 USD. Okay, now they've created an error event. Now what do? We need to punish them. They need to lose their eigen. That's the right punishment for them. How do we do this? Anybody can create a new fork of eigen, the token. They create a new fork of the eigen token. And now, in this new fork, they say, oh, we are doing this because of that pre-agreed condition that eigenstakers shall not give a wrong oracle report. So now, those stakers who gave the wrong oracle report, 1 BTC is equal to 1 USD, their stake is removed from the second eigen token. The new eigen token is created. So now looking outside looking from inside Ethereum, Ethereum doesn't know whether eigen 1 is correct or eigen 2 is correct. Both look the same to Ethereum. It's just another ERC20 token. But looking from the outside, we know the pre-agreement on what is the eigen token is the one that says the truth. Okay? So people converge on eigen 2 as the token that is valuable. When people are trading it, they're going to trade eigen 2. When people are staking it, new services come in, they would want eigen 2 to be staked, not eigen 1. So this is the core idea. The fact of whether eigen 1 is right or eigen 2 is right is not transparent on-chain, but it's transparent off-chain. And we want to bring that intelligence on-chain to turn around the crypto economics. You want to enforce the correct punishment and rewards. Okay, on the eigen users, point to the right one. So this is the core idea. There is more to it. This doesn't overload Ethereum's social consensus because Ethereum doesn't need to know what is going on. Only anybody who's interested in the eigen token needs to do this. This is not the idea that tokens can be forked is not our original idea. Vitalik wrote about this back in 2014. There was a paper even earlier called TruthCoin, and a bunch of blog posts here. The main system that worked off this idea is called Augur, which used this idea of token forking. But it had a bunch of shortcomings. I'm not going to get into it, but I'll explain how we solve those shortcomings. So the first property that we have for eigen is it's universal. Universal. What do I mean by universal? It is not an application-specific forking token. Augur was an application-specific forking token built for prediction markets. Eigen is a universal forking token. So what that means is you can start building new tasks on top of the eigen token and create forking conditions for all of them. And if the eigenstakers opted into those conditions, they'll be bound by it. Okay, so universality is one major concept in the eigen token. The second one, which actually makes this insanely hard, is what we call a property called isolation. Isolation is if a token is forking willy-nilly, that same token is listed on exchanges, the same token is being lent and borrowed, there's financial applications on all these tokens, it induces a downstream cascade of events that you don't want. So the way we solve it, we create two kinds of eigen token. One called a solid representation. A solid representation is one which is honored 1:1 on every eigen fork. If you hold a solid representation, it's honored 1:1 on every eigen fork. But if you hold a not solid representation, which is forking representation, then you are stuck with that fork, but you need a forking representation to stake. So what we do is we decouple the utility of the eigen token on fork staking and financial utility with 2 different tokens. And then finally, or the third point is metering. Metering is forking induces a social cost. Somebody comes in and says, hey, there are two eigen tokens, they can be forked. Now this is a problem, because now everybody needs to adjudicate whether eigen 1 is correct or eigen 2 is correct. Induces a massive social cost. You don't want that. What are we going to do about that? We meter the cost of social consensus. Let's say we know, this is going to induce X amount of pain on all the users. What you do is you say, when you fork the token, you have whoever is claiming to fork the token, they have to burn a bunch of the first token, the original token, and they will be minted the same amount or more in the second token. So they are actually measurably giving up opportunity cost. If the first token turned out to be right, they're burning their fingers. This is a kind of a bloodletting in making sure that they are actually do not create denial of service, but also if they were wrong, the value of the other user's eigen token increases, compensating them for their attention. Okay, so that's metering. And then finally, we found a major problem in cryptoeconomic security, which is cryptoeconomic security models usually were adversary-centric, which means they think about whether an adversary, they think about what is the profit that an adversary can make from attacking the system, and what is the cost incurred on the adversary. It's called cost of corruption and profit from corruption for an adversary. But the problem with these things is there are always extrinsic incentives that you can't model. Somebody may have a short position, somebody may be bribed, somebody may have some other thing going on. You can't model all of this stuff. So we created a new framework we call strong cryptoeconomic security. Strong cryptoeconomic security is adversary neutral. You don't need to think about the adversary. You think about yourself as a user. And the way you do it is if you're transacting certain value on the system, you buy insurance directly from the system called compensation. And when the stakers are slashed for their misbehavior, you can take that stake and compensate back the people who hold the insurance. So if I'm using an Oracle in a DeFi protocol and I have risk worth 1 billion, if I hold insurance worth 1 billion from the protocol, then I'm cryptoeconomically secure, irrespective of what the adversaries do. So this is a brand new concept of cryptoeconomic security that we invented called strong cryptoeconomic security. The eigen token satisfies all these properties, solving this fundamental problem of how to do strong cryptoeconomic security for arbitrary intersubjective faults. Thank you so much.
Okay, we have time for maybe one question.
Just trying to understand from the Ethereum Classic fork perspective, the only proposal here is you would have to burn a bunch of tokens before you can mint eigen 2 tokens? Or is there something else?
There is all the 4 differences that I laid out. The first one is Ethereum versus Ethereum Classic. The problem was the setup condition of Ethereum was code is law. Code is law. And then what we had to do was to negotiate that code is law except there are major bugs. So this was a massive social renegotiation, very hard. Second one is Ethereum does not fork for arbitrary events. And to fork for arbitrary events, you need a mechanism to solicit and monitor the cost of forking and the total amount at risk for all these different events. So that goes to the first point of universality. The second one on isolation, which is also a very important thing, which is how do you make sure that there is a single representation that is honored 1:1 on all these different forks. There's a whole bunch of details on this. I'll let you take a look at that. And then finally, slashing and redistribution is a new concept for how you honor people who are actually using the system without letting them make random assumptions on adversaries. So those are all the differences. Thank you so much.
Thanks, Sreeram.